All right, well, good morning, everybody. Let me do a little screen share. Okay, so I got her zooming. And then I got this other thing here. I never know which one to do. I'll do that one. That might be right. Today is what? Thursday, November 5th? We got a president yet? Anybody in here want to be president?
No.
Well, shoot, we're up a creek now, aren't we? Okay.
Now?
No. Hey, this is all on you. You guys got to fix this mess. My generation screwed it up. It's yours now.
Or we could just ignore it.
That didn't work.
Well, I mean, it did not work. We're still
Okay.
here.
Okay. I'm voting for him. Do I have a pen? Can everybody at home hear me and see the green screen? We decided today was Thursday,
Yes, it
November
works.
5th. So I set up, was that a yes or no on everybody hearing me and seeing me? Where's the little chat thingy?
Yes, it works.
Oh, come on, where's my little chat thingy? Hey, good morning. Beautiful day. Okay, go away. Let that small. Let that small. Where'd the chat window go? That's not it. Stay open. Not big. There we go. There we go, there we go, there we go. So I put up a new web work with the word problems on it and then the beginning of section 5.1. We're done with chapter 4. Does anybody want to start by asking web work questions? Saving it for the big weekend, huh? No date this weekend again? What's up with that? We got the long day today. I think in the long day I can cover the rest of the course. Then we just take the rest of the semester off. Nah, you'll be missing me when I'm gone. No questions. What about anybody at home? Any web work questions? I'm good. I'm good. Okay. Okay, section 5.1 is what we're going to do. Let's see what the title of section 5.1 is with my little blind eyes. Does anybody at home want to be president? We're looking for one. Okay, we are doing section 5.1. We're going to talk about anti-differentiation. So we're going to reverse the order of integration. Reverse integration. Reverse differentiation. Come on, give it a try. So we will find, so our task, given the derivative of some function, find the function. It's kind of like Jeopardy, where you got the answer and then you have to come up with the question. So it's a little calculus Jeopardy. So for instance, what function has as its derivative so the first one will be, I don't know, start easy, 2x. or we're playing it Jeopardy way, this function has as its derivative 2x. And your question is, what is x squared? So the answer is x squared. All right, is that the only function whose derivative is 2x? Yeah, x squared plus any number, right? The derivative of constant is 0. So if I said what function has as its derivative 0, you would answer any constant. So if I had a function that looked like an x squared plus some sort of constant, then we have another function that has that as its derivative. So we'll put the constant up here. Let me denote the constant with the letter C. This will be called the most general antiderivative because it takes into account that 0 is added to every function. All right, so what function has as its derivative 10x to the 9th? There we go, x to the power of 10 plus c. All right, what function has as its derivative about x to the 5th? There we go. We know that when you take a derivative, you bring the power down and raise it to 1 power less. So I had to start with an x to the 6th power. But I don't have a 6 here, so I have to take it out over here by putting a 1/6 right here. So that 6 times 1/6 would give me the 1, and then I would have the x to the 5th, and then that arbitrary constant to get the most general antiderivative. So in particular, if I have a x to any power up here, at least a nice whole number, what's the steps that we do to reverse the derivative? What did we have to have as the function whose derivative ended up with an n as the power? How are these numbers related right here? One more, that's right. And then I've got to get rid of the number in the front that would come from taking the derivative of that. If I bring the n plus 1 down, I need to cancel it. So we would cancel it by a 1 over n plus 1. That's going to be called our power rule for antiderivatives, and I'll write that down shortly. So let's see if it works. What if I had an x to the negative 1/3 here? Try to use that little power rule over here, and let's see if we can come up with a function whose derivative has an x to the 1/3 in it. Or x to the negative 1/3 even. So the little formula that we came up with here says add 1 to it. So 1 plus a negative 1/3 will give me a 2/3. And then if I put 1 over 2/3 here, that's the same as a 3/2, isn't it? And then the arbitrary constant. But let's check. Let's take the derivative of this. Take the derivative with respect to x of 3/2 x to the 2/3 plus that constant. We would hang on to the 3/2. Then we bring the 2/3 down in front. Then you subtract 1 to get the negative 1/3. And then the derivative of the constant is 0. These two guys multiply to give me 1. And so I do have the x to the negative 1/3. So we're going to call that our power rule. The most general antiderivative of x to the n is x to the n plus 1 times 1 over n plus 1 plus that arbitrary constant. But now I don't want to use so much words. I mean, this is a math class. Let's get the words out of the math class. Get the numbers out of here, get the words out of here. Just start manipulating symbols. So let me give you a definition, then we'll use that definition. So given a derivative the most general antiderivative of little f is, we're going to denote with a capital F plus that arbitrary constant, where the derivative of capital F gives us back little f. So these were the columns over here for the little f of x's, and these were the capital F of x's. The process of finding an antiderivative all right, I got no colors. That pen is gone. Process of finding a derivative was called differentiation. The process of finding an antiderivative is anti-differentiation. Well, that's a big old long word. It doesn't even get you many points in Scrabble. Instead of calling it anti-differentiation, we're going to call it the integral of the function, and we're going to write it in the following way. F is the function that is the derivative of something, little f. The process of finding its antiderivative is going to involve this little symbol. It's going to be related in a way to a sum. That thing is called an integral sign. Then we have to tell you the name of the variable, because eventually you're going to get into calculus of several variables. So we put the name of the variable here with the differential of x. So this says the same thing as this sentence. Find a function that has as its derivative this guy. And what you do is you find that capital F plus the arbitrary constant. So this is called the integral of f with respect to the variable x. You need to know the name of the variable because sometimes in here we've got a constant. All right, so let's just go back through this. Let me back up a step. From our first page, we would write that the integral of 2x with respect to x is x squared plus the arbitrary constant. We would write the integral of 10 x to the 9th with respect to x is x to the 10th plus a constant. We would write the integral of x to the 5th is x to the 6th times 1/6 plus the constant. And so we would write our general power rule as the integral of x to the n dx as x to the n plus 1 divided by n plus 1 plus c. So finding an antiderivative is called integration. We're going to integrate functions to find functions whose derivative is the stated function. And when we learned how to take derivatives of functions, we had this definition, and then we use that definition to generate a boatload of rules. We're going to do that. We're going to write all those derivative rules backwards as integral rules. But first, let me explain the importance of this symbol here. Tell me what the difference is, say, between the integral of 5, I put dx here, the integral of 5 if I put a dt here, and the integral of 5 if I put a dz here. Whoops, come back. What's the difference between those three examples? What did we take the derivative of to get 5? Here we took the derivative of 5x, because this says our variable of interest is an x. Well, what about here? I didn't take the derivative of 5x if I'm doing things with respect to t. I took the derivative of 5t. And likewise here, my function is a function of z. So here I would get 5z plus c. So it tells us the name of the variable. And then, like I said, when you're in Calculus 3, you're going to have functions of several variables in here, and then you'll have a list of differentials out here. And one at a time, you compute something called an iterated integral. All right, so let's think of all of our derivative rules and work our way backwards. So recall all of our derivative rules. We had 6 trig functions. Let's take their derivatives. The derivative with respect to x of the sine of x was the cosine of x. The derivative with respect to x of the cosine of x was minus the sine of x. The derivative with respect to x of the tangent of x, am I the only one that remembers this, or you guys remember them? Secant squared. The derivative with respect to x of the secant of x, secant tangent. The derivative with respect to x of the cosecant of x, negative cosecant of x, cotangent of x. And then finally, the derivative with respect to x of the cotangent of x. So negative something. Cosecant squared of x. All right, then we've got e to the x. The derivative of e to the x, e to the x. The derivative of the natural log of x was 1 over x. The derivative of, well, what else do we have? We have our inverse trig functions. The derivative of an arctangent of x is 1 over x squared plus 1. The derivative of the arcsine of x is 1 over square root of 1 minus x squared. and the derivative of an arcsecant of x is 1 over the absolute value of x times the square root of x squared minus 1. We had all those. So now I'm going to write the antiderivatives in the next column. These are all of our derivative formulas. One page. Oop, that don't do me. Close enough. That's a new feature. I didn't know that turned that way. Maybe I broke it. Oh, you son of a piece of paper. Okay, so those are the derivatives. Let's go backwards and write the antiderivatives. This says that if I find the antiderivative of the cosine of x, I should get the sine of x. So using the notation from a second ago, I would write that the antiderivative, or the integral, of the cosine of x as a function of x is equal to the sine of x plus the arbitrary constant. The integral of a negative sine of x should give me a cosine of x. So if I just put a positive sine of x here, I've got to adjust for the sine, the SIGN. If I leave this sign off, I'd put it over here, and that would give me a minus cosine of x plus c. This one says that the integral of the secant squared is the tangent. Integral of the secant squared of x as a function of x is the tangent of x plus c. The next one, I'm going to write that the integral of the secant tangent of x is a secant of x plus c. The integral of the negative cosecant of x times the cotangent of x is a positive cosecant. So if I leave this minus sign off, I've got to move it to the other side. The integral of cosecant of x times the cotangent of x is a negative cosecant of x plus c. Same deal here. I'm going to put this minus sign over here with the antiderivative so that the integral of cosecant squared of x is cotangent of x plus that arbitrary constant. Here's the easy one. The derivative of e to the x is e to the x, so the antiderivative of e to the x is e to the x. The derivative of the logarithm is 1 over x. The integral of 1 over x is the natural log of x, with one minor adjustment. Over here, we all know that the domain of a logarithm is all x values strictly bigger than 0. So this holds for x values strictly bigger than 0. But over here, this holds for all non-zero x. To make this well-defined, we put it in absolute value bars. Now they're defined at the same place. So the integral of 1 over x is the natural log of the absolute value of x. The derivative of the arctangent is 1 over x squared plus 1. So if you find the integral of 1 over x squared plus 1, you should get an arctangent. Same deal here. If you integrate something that looks like the integral of 1 over the square root of 1 minus x squared, you're going to get an arcsine of x. If I put a minus sign up here in the numerator, you can write that as a negative arc sign, or you can write that as an arc cosine. The integral of this little goofy thing is an arc secant. We had two more. We had exponential functions of another base, and we had log functions of another base. Let's see what those look like. The derivative with respect to x of any other number to the x. Let me use a number b. It did have a b to the x in it, and it also had something else. What else did it have? What's the derivative of 2 to the x? Anyone forgot that one? Let's figure out the derivative of 2 to the x. Let's use implicit differentiation. Let me turn the page over and we'll do that. If y is equal to 2 to the x, then the natural log of y is equal to the natural log of 2 to the x. Bring the x down. Now take the derivative. 1 over y times y prime. That's a constant. Copy it down. Take the derivative of x and get 1. So when I solve for y prime, I get y times the natural log of 2, where y is 2 to the x. So the derivative of 2 to the x is 2 to the x times the natural log of 2. That means the integral of 2 to the x natural log of 2 is 2 to the x. But if I just put this over here, then that means I would have to divide it out and put it with the antiderivative. And so it would look like this. The integral of b to the x has a b to the x in it, but it has a 1 over, which side should I put it on? 1 over the natural log of b right here. Oops, I just wrote the integral. I meant to put a natural log of b there. So let's take the 1 over away, and that's the natural log of b. Let's just take the whole thing away. The derivative with respect to x of b to the x is b to the x times the natural log of b, which says the integral of just this b to the x with respect to x has this b to the x divided by the natural log of b. So you're going to be able to recognize these, or at least think backwards to find them. The other two really important antiderivative rules were the same as our two differentiation rules. That if you had a polynomial and you wanted to take its derivative, you can do things term by term. And if there was a number stuck in front of the polynomial, you can pull it out, take the derivative of the term, put it back in. We have the same rules for antiderivatives. We have that if you want to take the antiderivative of two guys added together, you can do that one guy at a time. For example, if I wanted to integrate 2x plus the sine of x dx, then I can find the integral or the antiderivative of 2x, add to it the antiderivative of the sine of x. The function whose derivative is 2x was x squared plus a constant. I'm going to save that constant for a minute. the function whose derivative was the sine of x was almost the cosine of x. Derivative of cosine is a minus sine, so I would need a negative cosine of x here, plus a constant. Now I'm going to add the constant from here to the constant from there and get another constant. The good thing about integrals is you can always check your answer. You just take the derivative of your answer to see if you come back with the original integral. The derivative of x squared is 2x. The derivative minus cosine of x is a positive sine of x. The derivative of the constant is 0. Then if you have a constant times a function, you can ignore the constant, find the antiderivative of the function, and tack it on in the end. So for instance, if I want to find the antiderivative of 432 x to the 10th dx, then I'm not going to let the 432 bother me. I'm going to get it out of the way and then find the antiderivative of x to the 10th. And we find that one using our power rule, right? The power rule goes entirely opposite of the derivative rule. In a derivative, the steps you take are you bring the power down and then subtract. The antiderivative goes opposite in the opposite steps. To undo the subtraction, we add 1 to the power. To undo the multiplication, we divide by the new power. So we add 1 to the power and get x to the 11th, and then divide by that 11. These two put together tell us that an integral is a linear operator, just like a derivative is. In other words, I can write those two as the same rule, like this. Suppose I'm going to integrate some constant times f of x plus another constant times g of x, and I could have as many of these terms as I'd like. But we do things term by term, and we pull the constants out. Oops, I said pull it out. I don't have a pencil either. Don't have a red pen, don't have my glasses, don't have a pencil. So I get scribble marks in your notes. Pull the constants out, find the antiderivatives of the function, and then put them back on. So I can denote this as K1 times capital F plus K2 times capital G plus the arbitrary constant. And so, I sent you this through your mail in case you wanted to write on the handout. I sent you a list of problems that we're going to work in class. Anybody run those off? Do not, then you have to write them down. You didn't even answer my mail that I send you. I should have put a lot of heart emojis and stuff in the subject line so you don't get it up. Or like, warning, this email contains dirty pictures. Man, you'd be clicking like crazy, wouldn't you? There's a pair of dirty socks. There's a pair of scuffed up shoes. Here's all my dirty pictures. All right, let me make this bigger because I can't see, and I know you can. I can't even see the button that makes it bigger. Let's hit the little thingy here. It makes it bigger for me anyway. Okay. So we're going to try to apply all these rules to this thing here. And so what I said earlier was that we can do these things term by term. I'm going to put that step in, but eventually I'm going to skip that step. Here's what our first step would look like. These constants, the 3 and the 2, matter not. So I can pull this 3 out, integrate the x with respect to x, pull out minus 2, integrate e to the x with respect to x, and then I've got minus the integral of 4 dx. All right, our power rule applies to x to a power. Power here is x to the first. So it's the power rule, add 1 to the power and divide by that new power. So the integral of x to the first is x to the second divided by 2. Let's hang off on the plus c till the very end. Quick, quick, what's the integral of e to the x? Quicker than that. It's e to the x. And what about the 4 there at the end? What's the integral of 4? 4x. I'd take a derivative of a 4x to get a 4, and then we can put the constant of integration back here. You can put the 3 with the 1/2 together and write that as 3/2. Minus 2 e to the x minus 4x plus c. Again, you can check your answer. Take the derivative of that, and you should end up with this polynomial right here. So do the quick mental derivative. Derivative of x squared is 2x. 2x times 3/2 will give me 3. So 3 times x right here. Derivative of e to the x is e to the x, so I get a negative 2 e to the x. Derivative of 4x is 4, so I get that minus 4. And then, of course, the derivative constant is 0. Okay, so our power rule works for every power, not just whole numbers. It works for almost every power. Let's go back and look at the power rule. This power rule here, for any whole number n, we saw that we can do this. We can do that with fractional numbers. The only number that doesn't make sense on the right-hand side is when n is -1. So I'm going to put that disclaimer over here that n cannot be -1 because I can't divide by 0. But x to the -1 had its own rule anyway. Let's look at the function that had the x to the -1 in it. Wherever I put that. When x is -1, we have 1 over x. Where are you? There. When x is -1, that's the same as 1 over x, and we know the function whose derivative is 1 over x is the natural log of x. So that pops up in that next example. That's going to show up right here. Is that a -1 or is that just my eyes? And also, as we did with derivatives, when we had a square root sign, we start by replacing it with a fractional exponent. When you have an x in the denominator, instead of doing a quotient rule, we can move it up and change the sign on the power. So we have to make sure we've got things written as the form of the sum or difference between x's. So I'm going to start by writing that x to the 1/2 instead of square root of x. So I'm going to have first an x to the 3/2 minus 4 times the integral of x to the -1 plus the integral of x to the 1/2. So these two involve the power rule, add 1 to the power, divide by the new power. But this one is our logarithm. So let me show the step where I add 1 to the power. Let's move over here. I got 3/2 plus 1 here, but then I have to divide by that new exponent. This one we said was the logarithm. So here we're going to write that as 4 times the natural log of x. And then again, we're going to put it in absolute value bars. And for this third one, add 1 to the power, and then divide by that new power. And now we can do the arithmetic. 3/2 plus 1 is 3/2 plus 2/2. So that gives me x to the 5/2. If you divide by 5/2, you flip it over and multiply, so I'll have a 2/5 right out in front here. Here I'm going to still have the 4 times the natural log of the absolute value of x. 1/2 plus 1 is 3/2, so this becomes x to the 3/2. Now I'm dividing by 3/2, so I flip that over to get a 2/3 right there. And then when you're done, you put a little accent on it by adding the plus c. That's a 5, and that's a 3. Easy enough? All right, so knock yourself out on the next one, number 3. I'll come check your answer with you. Go ahead and do 3 and 4. So I can show both of those. So you should have them both by now. I'm going to put this right next to this. You can almost see both. There we go. I'm going to do this term by term. And so here, I'll put that. It's small again. Oh, not gone. All right, screw that. So here, when we're integrating cosine of x, we're right here at this step. The integral of cosine is a positive sign. Pull the 3 out and multiply that by sine. Pull out the -2. And now we're going to integrate sine of x. But the integral sine of x is a minus cosine of x. So I can put this now as a plus cosine of x plus c. Is that what you got? All right. What function has as its derivative secant squared? Well, it's the tangent, right? Integral secant squared is tangent. So this becomes 3 times the tangent of x plus c. All right, now we'll make you think backwards, and then we're showing you the answers. So the next one's quite the quickie as well. What is the function whose derivative is the product of the cosecant and the cotangent? It would be a negative cosecant of x. The cosecant is negative cosecant cotangent, so we put the minus sign over there. Connect those with an equal sign. Okay. All right, there's back side or a second page. And a back side. Oh, we got lots. Okay, we've got to do a little bit of thinking on this one. I know the derivative of e to the x is e to the x. But what if I stick a number up there with the x? I'm going to see this. I don't have my glasses. All right, there's an x over 2 and e to the 4x. So let's think. Let's think backwards. What's the derivative with respect to x, say, of e to the 4x? What do you do when you take the derivative of e to a power? So I get the e to the 4x back, right? And then what else? The derivative of the power gives me a 4. Okay, we've got to go backwards. If I want to find the antiderivative of e to the 4x, well, if I know this, that should give me this. If I want this 4 out of here, I divide it on both sides. So it says that the integral of e to the 4x is 1/4 e to the 4x. So let's write that now in general. Stick any number up here with the x, just a number. And that's got to be an x to the first power. And find the antiderivative of that. Well, we know we have to get the same function back. But then normally in the derivative, we would multiply by the k. So the antiderivative has to divide by the k. So let's make that a constant times x rule for e to the kx. So we've got those in both places here. You can think of x over 2 as a 1/2 x. So our k is a half. And that means if you integrate e to the 1/2 x, you should get 1 over 1/2 times e to the 1/2 x. When you integrate e to the 4x, you get that with a 1 over 4. But 1 over 1/2 is just a 2. So let's write that as 2 times e to the x over 2 minus 1/4 e to the 4x plus c. It only applies if that's an x to the first power up there multiplied by a constant. So you take the same function back, the reciprocal of the constant. Same function back, the reciprocal of the constant. It's a lot harder to find, say, the integral of e to the x squared. And so what function has that as its derivative? That was a little bit harder. All right, what are your thoughts on problem number 7? got a radical sign with an x squared minus 1 in it. Out front, I've got an absolute value of x. The 3's baggage, so I can just pull the 3 down. And then tell me what function has as its derivative that radical sign with the x in front of it. Which one? Arcsecant. That's an arcsecant. Like that. Okay. All right, here's another one for you. Try number 8. We got the integral of 3x squared plus the square root of x minus 1 over x integrated with respect to x. All right, let's see if we got it. We're going to start by taking the radical sign off and putting a 1/2 power. And then we can also write that as x to the negative 1 if you want, or you can leave it like that. But I can write that as the integral of 3x squared plus x to the 1/2 minus x to the negative 1. Then we'll use our power rule. If I add 1 to the x, to the power here, I get an x cubed. When I divide by the 3, they cancel. So this is just going to give me an x cubed right here. We're adding 1 to a 1/2. And so that's going to give us 1/2 plus 2/2 gives me an x to the 3/2. Then we have to divide by that. So dividing by 3/2 by flipping it over, we're going to put a 2/3 right here. If you try that power rule here, that'll give me an x to the 0 divided by 0. Can't have that. So that's the clue that this is the one that has its own formula. What function has as its derivative? 1 over x. That's a natural log of x. And we put the x in absolute value bars. Okay. All right, next one. When you have x's in the denominator, you can't just go down there and add 1 to the power and divide by the new power, just like we couldn't do that with derivatives. You have to rewrite everything so that it looks like a constant times x to a power, plus a constant times x to a power, and so on. So we've got to rewrite 3 over x squared as 3 times x to the negative 2 before we can apply the power rule. I can think of this 3 as a coefficient of 1/3. So let's write the next term as minus 1/3 x squared. Now it's set up in the right way that we can integrate term by term. The numbers in front don't matter. You can copy them down. find the antiderivative of the x, and then put the number back on. So be careful when the exponent's negative because you're adding 1 to the power. X to the negative 2 integrated gives you a new power of negative 2 plus 1. Give me a negative 1. And then I divide by negative 1. Next term has the minus 1/3 here. Add 1 to the power and gives me an x to the 3rd. But now I have to divide that out. And then we're at the end, so we can tack on a plus c. Now let's rewrite it with positive exponents. These two numbers just give me a multiplier of negative 1. So I have a negative 3 over x. These two will give me a 1/9, and it's a negative 1/9 x cubed. Everything okay out there? All right. Next one. I have a denominator, but the denominator is collective. So I can't rewrite that, say, as 1 over 1 plus 1 over x squared. I can't break up a denominator. You'll see on the next page, but we will break up numerators. If we don't break up denominators, that's not algebraically allowed, no matter who the president is. So you got to think, what function has as its derivative a denominator that is the sum of 1 and x squared? That one? The inverse tangent. That's the inverse tangent of x. That's it. Nothing magical about this. We just spit out the antiderivative. All right, there's more. Now I forewarned that we do break up the numerator. We do break up fractions in the numerator. We don't have an analogous quotient rule. We don't have a product rule for integrals. We have to write our integrand, the stuff inside the integral sign, as a sum. So I'm going to break this up first to look at as 1 over x to the 4th plus x squared over x to the 4th. Now I'm going to write those as x to a power. The first one is x to the negative 4. This middle term reduces to 1 over x squared, which I can now write as x to the negative 2. Now I can integrate term by term. Add 1 to the power, divide by the new power. So negative 4 plus 1 gives me a negative 3. This gives me an x to the negative 3, then I divide by negative 3. Add 1 to negative 2. Negative 2 plus 1 is a negative 1. Then we divide by negative 1. Back on the plus c when you finish the antiderivative. Let's make it look more pretty. This is a 1 over x cubed. I'm going to multiply that with the 1 over 3 and get a negative 1 over 3x cubed. This is a minus 1, and that's a 1 over x. So I can write it like that. Maybe write it like that. You can see it. Okay. Now the next one again, we can't break up a denominator. We certainly can't break up a square root. So you have to ignore the 10 and think about your list of derivatives. There's a function that has this thing as its derivative. It's got to be one of our inverse trig functions. Which inverse trig function has that one? Inverse sine? So this is 10 times the inverse sine of x. Finally, we've got this one. We've got things multiplied together, and we do not have a product rule. And when we first learned how to take derivatives, we had to spread out products, spread out quotients the best we could. We got to do that here. We got to FOIL this out so that we can integrate it term by term. We must multiply this out first. We've got to have a sum or difference every single time. So let's multiply it out. I'm going to send the x through the parentheses. X times 2x is going to give me a 2x squared. X times 1 gives me an x. Now it's the negative 4's turn. Negative 4 times 2x is a negative 8x. And negative 4 times 1 is a negative 4. We can put these two together and get a negative 7x in the middle. And now we can integrate term by term. Got to have plus and minus signs between your expressions. Okay, to integrate this, let's get the 2 out of the way here. And now to use the power rule on x squared. Add 1 to the power, divide by the new power. So the new power is x cubed, and I get a 1/3 here. Okay, I'm going to pull out the 7. What about the x? What's the antiderivative of x? 1/2 x squared. And now I've got the 4 on the end. What's the antiderivative of the 4? What did I take the derivative of to get 4? 4x. Let's get rid of those parentheses and write that as 2/3 x cubed minus 7/2 x squared minus 4x plus c. I think I'll be able to recognize these pretty quick after a while, maybe not so fast today, but hopefully by this afternoon. Have all these recognizable. I want to show you what that plus c might mean in some different cases. So let's look at a few more examples here. The graph of a function has slope of 4x cubed plus 2 at each ordered pair on the graph. The graph of a function has that as its slope, and this graph contains the point 1, 2. Find this function. So we have some function whose slope has that formula. In fact, the slope at the point 1, 2 would be 6. What was the function? So there's something that contains, I don't know. I'm not going to draw it. So what do you know when you're told the slope of a function? Anybody still out there? If I gave you a function and said find its slope, what's the first thing you'd do? Take its derivative. So there's the derivative of the function. So this says that our function, let's call it f, that f prime of x is 4x cubed plus 2. So let's work backwards and get f. We'll either write it in the integral sign or do that part in your head. What did we take the derivative of to get 4x cubed? And what did we take the derivative of to get 2? 2x. But then we also have a 0 hanging out here, and we know there's a certain constant that satisfies that. Now what this is a class of 4th degree functions. There's a whole bunch of them. Adding a number on the end just lifts it up and down in the xy plane. So we got some sort of 4th degree function that might look like, I don't know, something like this. We got a whole bunch of them. Lifted up and down. Now we got to find the one of these functions in the xy plane that contains the point 1, 2. In other words, the y value is 2 when the x value is 1. We got to find that particular lifter that puts it through that point. So now y is 2 when x is 1 gives this sentence that 2 is equal to 1 to the 4th plus 2 times 1 plus c. So I need to figure out what c is so that this side adds to 2. 1 to the 4th is 1, plus 2 is 3. My gosh, c has to be negative 1. So the function I'm looking for puts that negative 1 right here. Let me answer the question down here. F of x is x to the 4th plus 2x minus 1. So in general, an antiderivative can be represented by a series of parallel curves moving up and down the xy plane. That constant will identify which of the curves we're talking about at a particular point. Here's another example. A particle moves along the x-axis in such a way that its velocity at any point is a function of x. How about 6 square root of x plus x to the 2/3 if the particle is at 1, 5, oops, if the particle is at, how am I going to say this? If the particle is at S is equal to 5 when X is equal to 1, find the position of the particle. I should have used T's for time, huh? When X is, I need another number. There's not a number I can take the cube root and the square root of at the same time, other than that. I don't know. How about when X is 0? Fine, no question mark, just a period. The way we worked this before is we were given the general position of a particle and then asked to find or answer questions about its velocity. How is the position related to the velocity if you're given the position function? It's the derivative. The velocity is the derivative of the position. And so the position is the antiderivative of the velocity. So I'm using S to denote position. So I've got that the velocity is the same as S prime. So if I want S, I have to find the antiderivative of the velocity. That'll give us the velocity at any x. And it'll give it to us as a function of x. So what we'll have here is the position at any time x is going to be the antiderivative of 6 square root of x plus x to the 2/3. And as usual, replace the square root sign with a 1/2 power. And now we're going to find the antiderivative. So we take each of those terms, add 1 to the power, divide by the new power. And now I get rid of the integral sign. I'm doing that step. I add 1 to 1/2 and get 3/2. Then I have to divide by 3/2 and carry the 6 along for the ride. Over here, I add 1 to 2/3. So that's 2/3 plus 3/3 will give us 5/3. This becomes x to the 5/3. Divide by that gives me a 3/5 here. And now this guy is very important, this constant of integration. I can simplify this. 3 goes into 6 twice, and this 2 times 2 will give me 4. So the position S at any time x is 4x to the 3/2 plus 3/5 x to the 5/3 plus c. So in order to tell what the position is when x is 0, I need to know this value c. How do I find it? Somewhere up in this scribble, I've given you the position at a certain time x. We're going to use that to find the constant of integration. That constant of integration corresponds to the position at time 0. So we have that s is 5 when x is 1. So I'm going to put a 5 here or 1 in for each x. And I have 5 is equal to 4 times 1 to the 3 halves plus 3 fifths times 1 to the 5 thirds plus c. D continues. One to any power is 1, thank goodness. So we have 5 is equal to 4 plus 3 fifths plus c. I'm going to move those two over. 5 minus 4 is 1. Minus another 3 fifths is c. 1 minus 3 fifths is 2 fifths. So we go back there and put it in our position function. From the previous page, the position function is here. Position at any time x is 4 times x to the 3 halves plus 3 fifths x to, what is that number there? 5 thirds plus 2 fifths. And so at time 0, that'll be 0, that'll be 0, then we'll get 2 fifths. So there's a couple of interpretations of what that arbitrary constant means. It does play a role. So we need to keep putting it in there. So how many of you have done this before? None? All brand new? Good. What were some of our other interpretations? What did we use a derivative for? We did it for slope of the tangent line. Our derivative also gave us velocity, but in general, the derivative is any instantaneous rate of change. So if you know how fast something is changing, you can find what that something is at a particular instant. Okay? Geez, why don't you guys take a break? Take a lap around the building and wake yourselves up. Don't wake up cold. He needs to sleep. Lucas got the wall holding him up back there, baby. That's where sitting in the back comes in handy. Take a little break. We'll talk about other stuff. I don't know what because I can't see. Might be out of paper too. Look at that. Let's see. I got 2 sheets of paper there. Yep, that's where we end the semester in Cal 1. Hopefully we get that done before we take Thanksgiving break. We need to do that online. Yeah, 3 pieces of paper. One's really wrinkled. Let's see what else I can write on. I got some tests up here. Did you guys get your test back? Anybody in here today that needs their test back? I got them here if you want them. Right on that. That's a lot of that. Man, I need a colored term. Okay, we're gonna try this one here. It's a problem out of your book. Couldn't spell brakes the first time through. So that's where that blotchy mess came from. This is number 48, page 335. After its brakes are applied, a car decelerates at a constant rate of 28 feet per second squared. Compute the stopping distance if the car is going 60 miles per hour, which is 88 feet per second, when the brakes are applied. So they stick their foot on the brake, leave it on there. We want to see how far it travels before it stops. Driving along at 60 miles per hour, and X an instant, we hit the brakes, keep the brakes on, and then eventually we come to a stop. Don't know how long it takes to come to a stop, and I don't know how far I've gone. But I'm looking for a change in distance between the time when the brakes are applied and the time when the vehicle stops. So I need to find the position function at any time t. What we are told is the acceleration function is a constant at the time when the brakes are hit. So let's just say at time 0, the brakes are hit. So let t equal to 0 correspond to the time when the brakes are applied. We know the acceleration at that time is the same as the acceleration at any time because it's constant. It's at 28 feet per second squared. We know the car is going 60 miles per hour when the brakes are applied. So we know that the velocity at that time is 88 feet per second. So we kind of need to know how long it takes to stop and what the change in position is there. What we do know that if we have position S, that its derivative is the velocity, and then its second derivative, or the derivative of the velocity, is the acceleration. We're going to start from here and peel off a derivative to get the velocity function. Then we're going to peel off a derivative to get the position function. And we peel off the derivatives by taking antiderivatives. So we're going to start with this. We're going to start with the fact that the acceleration at any time t is 28. And so the velocity at any time t is the antiderivative of the acceleration. So we're going to take the antiderivative of 28t, 28 with respect to t. It's decelerating, so we should actually make that negative, shouldn't we? So what would you write in general as the velocity function? What's the antiderivative of the negative 28? Negative 28t plus constant. What does that constant have to be? If I know the velocity at time 0 is 88. V at 0 is 88, so that means that when that t is 0, this has to be 88. So I have 88 is equal to negative 28 times 0 plus c. C is that initial velocity. So the velocity at any time t, for this example, is negative 28t plus 88. So far, so good? Okay. Then let's go backwards one more time. We've got the velocity. That's the derivative of the position. So to get this position, we take the antiderivative of the velocity. So the position is the antiderivative of the velocity. We take the antiderivative, negative 28t plus 88 as a function of time. Now, what's your problem here? Okay. So we're going to add 1 to the power. Power up here is a 1. The antiderivative t, the first power, is a t squared over 2. Put that next to the negative 28. The antiderivative of 88, what is that? What will we take the derivative of to get 88? 88t plus another constant of integration. So the position at any time t is equal to negative 14t squared plus 88t plus c. Well, we've got the position. Now we need to compute a stopping distance. So the stopping distance will be the difference in the position at the time that it takes to stop minus the time that the brakes were put on. So we need to find the difference between s at the time when we are stopped minus s at 0, the time when the brakes were applied. how are we going to find the time at which this vehicle is stopped? Set velocity equal to 0. So we need to take a backtrack to our velocity function. The time that the vehicle was stopped is when the velocity is 0. Need some room here. Time for stop is when the velocity is 0. So let's go back up a few lines to our velocity function. That's this one. We want to know t when velocity is 0. So we're going to solve this equation. 0 is equal to negative 28t plus 88. So if I move the 28t over here, and then divide 88 by 28, let's see. 4 times 7 is 28. 4 times 22 is 88. If I knock out a 4 everywhere, takes 22 over 7 time units, I guess, per second. 22 over 7 seconds to stop. So now we need to find the position at 22 over 7 minus the position at time 0. Uh-oh, let's use my wrinkled piece of paper. So the position at time 22 over 7 minus the position at time 0 using our position function from this line here. So here we're going to get negative 14 times 22 over 7 squared plus 88 times 22 over 7 plus c, that number, minus s of 0, but s of 0 will give me a 0 here, a 0 here, s of 0 is just c, which is nice, those are gone. And so there's our answer. What would the units on my position be? Feet. I'm not crunching numbers. We're just going to have to like that number just the way it is. Negative 14 times 22 over 7 squared plus 88 times 22 over 7. It would be nice to have that number because supposedly this is realistic. I want you to see how long it takes to stop if you're going 6 miles an hour, how far you travel. Have I got a calculator to calculate this? About how much?
138.
So you did the squaring and all that? 138 feet. At 138 feet, we're going to say 140 feet. Oh, that's 2 feet. How big is a car? A car is 6 feet long. That's more than 20 car lengths for you to stop. So as a mother, I'm very concerned about you